Hi everyone, welcome to this video. I'm going to be speaking about the pancreas, islet of Langerhans, glucagon, insulin, somatostatin, and all that fun stuff in this video. So I'll just go ahead and give you guys a brief overview of the pancreas. Actually, before that, I would like to say, before actually looking at the human body and anatomy, I thought the pancreas was shaped more like the liver, and like we know, the liver is shaped kind of like this. So going into anatomy, I thought the pancreas would look something like this as well. I was taken by surprise because the pancreas is actually more longitudinally shaped, like kind of like this one. I'm not the best artist, but it's more longitudinal shaped. So that was a good surprise, or just a surprise for me that you guys may also experience one day. So within the pancreas, I've drawn these islets, or like these clusters of cells that are distinctly different from the other areas of the pancreatic tissue. And these islets are basically clusters of endocrine cells. Clusters of endocrine cells. So pancreas does a lot of things in regards to digestion for us, right? But it also has a lot of other things that it participates in and it contributes to, and these endocrine cells are a big part of that. So I'm going to draw these islets a little bit bigger over here so we can just dive into it and see what else is going on over here. So these islets of Langerhans are going to have three different cell types. So we have the alpha cells, the beta cells, and then the delta cells. So alpha cells they're all going to secrete different things and then be responsible for different things. So alpha cells are going to be secreting glucagon. Beta cells are going to secrete insulin, and then delta cells are going to secrete somatostatin. Okay, so glucagon is going to be released in response to low blood glucose levels. So basically, if it's going to be released in response to low blood glucose levels, then we know that its action is going to be somehow to increase blood glucose levels. Insulin, on the other hand, is going to be secreted in response to higher blood glucose levels, and its action is going to be to get all the glucose into the cells, into the organs that it needs to go into, and in response, it's going to decrease the blood sugar levels. And then somatostatin has two distinctly different actions. Both are very, very important. Somatostatin within the endocrine system is going to within the endocrine system, somatostatin is going to inhibit the release of growth hormone, basically. And then within the GI system, somatostatin is going to inhibit gastrin and all these other GI hormones. Basically, I would just like to say somatostatin is going to inhibit all GI hormones. So this is just that brief little overview in regards to the islet of Langerhans. And how are these cells structured within the islet of Langerhans? I'm going to show you that right over here. So the islet of Langerhans is going to be structured in such a way that you have these alpha cells surrounding the beta cell. And then the way I like to remember it is just to think about how, in response to us eating anything at all, we have insulin released by our body to put all that glucose into the cells so the cells can function, cells can do their thing. That's why the beta cells, which is going to release insulin, is the special one, because it's very, very important to eating. Eating is a very, very important task for us human beings. So I just like to think the beta is the king of everything, and the beta is going to be, or the queen of everything, and it's going to be in the central area. And then you have these alpha cells that are surrounding it, and then you have these delta cells that are just interspersed in between them. So you have more alpha cells surrounding this beta cell, and then delta cell just in between. More alpha cells, beta cell. And then you get the picture. Basically, the beta cell is in the middle, which is going to secrete insulin, and then the alpha cells are going to be surrounding the insulin. Alpha cells are going to secrete the glucagon, and then the delta cells are going to be interspersed in between those circular areas and clusters of alpha and beta cells. I also wanted to kind of touch on the action of insulin and what it actually is going to do. So I'm going to erase this very, very quickly, and then talk about that very briefly. So we know that insulin is very important. We know that insulin plays into the pathogenesis of various diseases. It plays into the pathogenesis of diabetes, which is very, very prevalent within our society and community and our world, and therefore it's very important for us to understand the pathogenesis of diabetes and relating to insulin. So insulin is going to be released in response to in response to high glucose levels, right? High blood glucose levels. And when do you have high blood glucose levels? After you eat. So in other words, after you eat, another way to word that is postprandially. So postprandial. So insulin is released. Now you've just eaten a very, very nice meal, and then your body is releasing all these insulin from your beta cells of the pancreas, and you have insulin in your bloodstream because of the high blood glucose levels. So insulin is going to function to, the action of it is going to be, the action is to decrease the blood glucose levels, right? So how is it going to decrease that blood glucose level is what we're going to talk about right now. It's going to decrease the blood glucose levels by, it's going to decrease the blood glucose levels basically by increasing the, uptake by various cell types. And those cells can use glucose for various reasons, right? And another way to think about it is, if you want to decrease the blood glucose levels, if you're putting it into the cells, you're basically going to store it so you can use it for another time. If you just eat and if you're going to sleep, you're going to be fasting for the 8 hours. So you're going to need some energy from somewhere for your brain to work, for various other things to work and take place while you're sleeping. And even if you're fasting, you're still going to need a reserve of glucose, glycogen, and lipid and all that stuff, so you can still function as a human being. So increased uptake by various cell types. So number one, you're going to store it, right? So storage. And storage can be in various cell types. And most importantly, I'm just going to touch on 3 different cell types in which the insulin is going to act to increase storage. I'm going to keep this part because the main goal of insulin is to decrease blood glucose. And now we're going to talk about how it's going to do that through storage. So we have number 1, number 2, and number 3. So number 1 is just going to put it into adipocytes. Adipocytes is just a fancy term for lipid and fat and all that fat that I have in my belly and everyone has in their belly, and it's important for thermal regulation and various other things. So let's think our fat very, very briefly. So it's going to basically go into those adipocytes and then cause glucose metabolism. Basically glucose is going to cause glucose metabolism. And it's going to increase fatty acid synthesis, really resulting in more fat synthesis. And the interesting thing is that insulin is going to inhibit lipolysis, which makes sense if you think about it, because inhibits lipolysis because the main function is to store it. And if you want to store it, you don't want to break things down, right? Obviously it's always in equilibrium, right? Catabolism and anabolism is always occurring in equilibrium, but when you have glucose, your body's not going to want to waste that stuff. Your body's going to want to store it, and if insulin is the hormone that's acting in, you're not going to want to just get rid of things when you're actually building things up. So basically, you're going to be inhibiting lipolysis and increasing fatty acid synthesis. All right, and the next organ is going to act on, I say organ, but next thing, next whatever in our body that it's going to act on is going to be skeletal muscle. So we know that our skeletal muscle has a reserve for glycogen if we so may need it. So in skeletal muscle, it's just going to import the glucose in, it's going to do glucose metabolism, use up whatever it can get, and the stuff that it doesn't need is going to cause glycogen synthesis. And glycogen is just a storage form of glucose. And then we're going to talk about the liver. We can't talk about insulin or glucose or glycogen or any of that without the liver playing into the picture. So in the liver, it's going to cause glucose metabolism, and the same things as the skeletal muscle, glycogen synthesis, but it's also going to cause, so same thing as that, but it's also going to cause triglyceride export. And that actually makes sense because if it's able to export, then it's going to contribute to that fatty acid synthesis, and you can go onto the adipocytes and just help that out over there. One important thing to know in regards to the liver is that insulin itself has no power to control the transport of glucose to the liver. So in itself, insulin is not going to be the trigger for glucose to go into the liver, because the liver, think about it, the liver is going to spread glucose out to everybody in your body, and then it's going to be the selfless one getting the glucose last, only if everyone is supplied. So liver is basically just like the last resort for glucose, because it's selfless. Liver is very, very selfless, and it's going to make sure that everyone has its share of food, basically glucose, before it gets to do its glycogen synthesis and all that, glucose metabolism and all that stuff for itself. So that's interesting. Another thing insulin is going to cause, it's going to cause amino acid uptake, protein synthesis, which makes sense. Glucose is insulin is an anabolic hormone, right? Glucagon is a catabolic hormone because it's going to basically cause increased blood sugar levels, and it's going to do that by metabolizing glucose, and it's going to catabolize that and result in the increased blood sugar levels that we see. Insulin, on the other hand, is an anabolic hormone. It's going to build up fatty acids, it's going to build up adipocytes, it's going to build up our store for glycogen synthesis. It's going to build up our store of glucose by increasing glycogen synthesis both in the liver and the skeletal muscle. So I'll just write that over here in case anybody wants that clarification. Insulin is going to be anabolic. And then we have glucagon. I always get those mixed up. Glucagon is going to be catabolic. All right, so another thing with insulin is that it's going to increase sodium potassium ATPase activity. And like we know, sodium potassium ATPase is basically it takes part in so many reactions within our body, so it's very, very important. And if insulin is upregulating this sodium potassium ATPase activity, then there's actually various consequences of this. And another thing to note, I'm going to erase this very quickly, is it's going to affect potassium in a way. So we know that potassium, the majority of our storage of potassium is going to be intracellularly, right? So let's just say this is our cell right over here, and then, so this is intracellular, this is extracellular. So we have a very, very high concentration of potassium inside the cell than we do outside the cell, okay? And this is so that various things can take place within our body, and insulin itself is going to play a role because insulin is going to be the one that's going to make this homeostasis happen. Basically, insulin is going to promote the flow of potassium intracellularly. Okay, so without insulin, you're going to have more potassium ions on the extracellular side of things than you do on the intracellular side of things. But insulin is basically, just main point over here is that insulin is important in the maintenance of intracellularity, if that is even a word, for potassium. Basically, it's going to maintain the intracellular flow and intracellular nature of potassium being inside the cells than outside the cells. And that's going to have various consequences in terms of pathogenesis of certain things, like insulin resistance and diabetes, obviously. So I think I'm going to end the video there. Thank you guys for watching along. I'll see you guys in the next video.